All right, now we're in this investigation of the mean value theorem, and I must tell you that there are a couple of consequences that are pretty important for the mean value theorem, or corollaries. And a corollary is a statement that follows something that we know to be true. So here's a couple of them, starting with this idea of an increasing and decreasing function. If a derivative is 0 at each point on an interval, then f, the function itself, is increasing, or f increases on that interval. Now that makes a lot of sense, because if you have a function that is increasing on some interval, then you can say that its tangent line is going to have a positive slope. And if you remember, of course, the derivative being, the slope of a tangent line, that's going to signal that it's a positive derivative and therefore an increasing function. And you could make a similar argument for when f prime is negative, that it will decrease on that same interval. Now, a function that is always increasing or always decreasing on an interval is said to be monotonic on that particular interval. Not a vocab word that gets a whole lot of airplay, but something that will come up here and there. So good information to know. It's going to look... Now, where can we find if a function is increasing and decreasing? Well, we can find that information by determining where the derivative is positive and negative. We should note that f is both continuous and differentiable, which is good news. But how do we find out where it's increasing and decreasing? Well, strangely enough, one of the nice strategies is if you know where it's 0, then you know where it is not increasing or decreasing, and maybe you can go from there. So let's find the critical points first. And I know that f prime of x is 3x squared minus 4. And now I can go about the task of finding out where the critical points are by setting this derivative equal to 0 and solving for x with a few algebraic steps. And after you get a little bit of, I guess what we're looking for is rationalization. I almost said renovation because I think I have that word on my brain a lot this spring. It's going to look a little bit like this, plus or minus 2 root 3 over 3. Those are going to be your critical values. So in order to help us figure out where this is positive and negative, what I'm going to do is I'm going to make what's called a sign chart. And some of you already know about sign charts. It's really a big number line. And I'm going to mark off a couple of places on this number line. And one of them is going to be my lower critical value, negative 2 root 3 over 3. And one is going to be my bigger critical value. And what I need to do is I need to pick values of x that are in between and also on either side of my critical values. And I'm going to dump them into my derivative to help me figure out what's what here. So the first point I'm going to go with is one that's dead in the middle. We're going to go with 0 because that's an easy one to test. And if I go to find f prime of 0, I discover it's going to be negative 4. Now remember, I'm putting it into f prime. That's a big thing there. So if f prime of 0 is negative 4, then everything inside that interval is going to be negative. Now let's go ahead and do the same thing for a number that's bigger than 2 root 3 over 3. And I'm going to pick the number 3 because I know that that's definitely bigger for sure. And when I go to find f prime of 3, I'm going to end up getting something that is, okay, well, let's see, 3 squared is 9 times 3 is 27 minus 4. That's 23. So that's going to be positive. And now I need to do the same thing by picking a number that is less than negative 2 root 3 over 3. I'm just going to go with negative 3, and you're going to find out you get the same thing. So now by completing this little sign chart, we now know that where the function is increasing and decreasing. It is increasing where the derivative is positive, and that's going to be from negative infinity to negative 2 root 3 over 3, and also from 2 root 3 over 3 into positive infinity. And it's decreasing on the interval in between those two critical values. That is good information to know. So like I said, if you find out where it's 0 first, then you can figure out where it's positive or negative by doing those particular things. All right, let's take a look at some more ideas here. Every point, if a derivative is 0 at each point, then there is a constant function for which f of x is equal to that constant. Well, that makes a lot of sense because all functions that have constants have derivatives of 0. Okay, but this also opens the door to something really interesting. It asks the question, it says, wait a second, hold on. This means that there are many different functions that all have the same derivative. Oh, well, I wonder if that's possible for other pairs of functions. And the answer to that question is sure there is. I mean, maybe f of x is equal to sine x plus 5, and g of x is equal to sine x minus 7. Maybe we have an f of x that is e to the x, and a g of x that is e to the x plus 3. Both of those have the same derivative. Or maybe what we have here is a situation where it's f of x is equal to x squared minus 4, and g of x is x squared plus 6. In each and every case, all of these functions have, pairs of functions rather, have the same derivative. But what's the difference? Well, the difference is these constant numbers out here. These constant numbers indicate that they're going to drop out whenever we take derivatives, and that makes a lot of sense now that we hear it. So that opens the door to this idea. A function big F of x is called an antiderivative of a function little f if big F prime is equal to little f for all of its domain of f. And $15 word alert. The process of finding an antiderivative is called anti-differentiation. Now, I had a teacher a long time ago that would call that a $5 word. I guess inflation has taken over. That's why it's a $15 word now. And we now know that if f has one antiderivative, then it has infinitely many, and all of which differ by a constant. So we are able to find a particular antiderivative, and I'll get to that example here in just a moment. But the way that we do this is we have to think backwards, and we have to think about all our differentiation relationships to make this happen. So let's take a look at something pretty simple and straightforward here. If I found the antiderivative of 6x squared, well, there's a whole bunch of those that we could find. And my big F antiderivative here, what function produces a derivative of 6x squared? Well, probably 2x cubed, because if you take the derivative of 2x cubed, you should get 6x squared. Now I'm going to have to tack on a constant. Do I know specifically what that constant is right now? No, I don't. But I could probably find it out if I had a little bit more information. Okay. What about all the functions, whose antiderivative is cosine of x? Well, that's going to be pretty easy to do. It's all the functions that have a sine of x plus some unknown constant that will drop out when we differentiate. So now you're getting the idea of finding an antiderivative here. all the functions. Okay, now what if I wanted you to find the derivative function whose derivative is sine and whose graph passes through the point 0, 2? All right, the steps are pretty easy here. We're going to find the antiderivative function. We're going to sub in 0 and 2, and then we're going to solve for c. So let's see if we can figure this out here. Okay, we know that little f of x is going to be sine x. So our antiderivative has got to be negative cosine of x plus c. Well, how do we know this? Because the derivative of negative cosine is positive sine. Now what I'm going to do is sub in 0 and 2 and solve for the c. 2 goes in for big F, and the 0 goes in for x. And now I'm able to figure this out. The cosine of 0, of course, is 1, but there's the negative. So my c value works out to be 3. So the final answer here, our antiderivative, is going to be negative cosine x plus 3. That's the specific one that works here. All right, that should wrap up this one.